Game.
I will be discussing about the specifications and estimates.
Geothermal energy. It is the energy or heat within the earth. The word geothermal comes from the Greek word ego, meaning earth, and therme, meaning heat. Many people around the world use geothermal heat or energy to produce many different kind of energy, such as electricity, to heat up buildings, greenhouses, and different kinds of purposes. At the base continental crust, temperatures are believed to range from 200 degrees Celsius to 1000 degrees Celsius, and the heat is transferred towards the surface mostly by conduction. In some areas, the heat gets closer to the surface due among others to intrusion of molten magma. Example of this is volcanic eruption, where the magma breaks the earth's surface to form a lava. So lately it has been obvious of geothermal energy due to eruption of Taal volcano. Next is to high surface heat flow due to a thin crust. Sample of this is when heat transfers from the core through convection to heat up buildings. Typically like that. Third is or to ascent from or of groundwater that has been heated. Sample of these are hot springs where heat from the core of the earth escapes through springs or hot springs or bodies of water beneath the mountains. The exploitable geothermal systems can be broadly divided into high temperature fields where it is greater than 180 degrees Celsius, where volcanic activity takes place, and low temperature fields less than 180 degrees Celsius. Estimates. So I'm gonna show you a picture of world map where geothermal energy can be produced by digging up. So based on the illustration, the red spots on the world map have high temperature with a deepness of 100 meters down. This shows that the higher the temperature, the more geothermal energy or heat can be collected. This is the map of the Philippines. And based on the previous illustration, this map shows the spots in the Philippines with the highest temperature with a deepness of 100 meters below. It also means that the higher temperature of the said spot, more geothermal heat or energy can be collected. Bottom line of these estimates is that geothermal energy can hardly be measured without digging up the Earth's surfaces.
Exploration and extraction. Geothermal exploration searches the Earth's subsurface for geothermal resources that can be extracted for the purpose of electricity generation. Geothermal exploration is commonly separated into phases, a set of techniques that the developer will use to determine if a location is worth investigating further. Many geothermal developers define phases based on economic considerations and permitting requirements. Phase 1. Regional reconnaissance. Techniques involved. Geothermal literature reviews help improve exploration efforts because by knowing the history of what has already been done and what worked or didn't work, multispectral imaging has been used to detect and map relative mineral determinations, shallow subsurface thermal anomalies, and abnormalities in vegetation. Phase 2. Prospect evaluation. Techniques involved. Compound and elemental analysis. By taking appropriate samples of fluids from surface springs and from well discharges, a great deal can be learned about the presence or absence of a geothermal resource. Geothermometry. It is used to estimate reservoir temperatures for most of the systems. Phase 3. Project appraisal. Techniques involved. Electromagnetic technique can be used for monitoring of circulating fluids in reservoir and thus provide important information about their activity and fluid content. Joint inversion technique. It is where multiple geophysical datasets are processed simultaneously to produce more realistic estimates. Phase 4. Exploratory drilling. Techniques involved. Site preparation and infrastructure. Once a drill site has been selected and surveyed, the necessary lines for electric power supply, water supply, and waste disposal need to be organized. Drilling operations. The normal drilling operation starts after the site construction is finished, with the move and rig up of the drill rig. Drilling equipments. These items are used to rotate the drill string from the surface to the bit on the bottom. The Kelly bushing transmits the rotation onto the Kelly, which allows traveling the string up and down in the rollers of the Kelly bushing. This device has a built-in engine to rotate the drill string, and allows traveling and rotating the string without the need of a Kelly. However, very often a rotary table is installed as a backup for the top drive. Drill bits are tools to destroy the rock. The selection is made according to the rock types and properties, and the applied drilling technique. Some tools are shown in figure 3.5. Drill collars are used to generate the weight on bit, to assure penetration of the bit cutters into the formation to be drilled. Rotary steerable systems allow steering while rotary drilling, that is, with the continuous rotation of the wool drill string. Geothermal energy extraction, handling, transportation, and storage. To extract geothermal heat, the hot water is pumped out of the deep subsoil, and the heat is extracted using a heat exchanger. The cooled water is then pumped back and eventually heats up again. Geothermal energy can be used for heating and cooling purposes, or be harnessed to generate clean electricity. Normally, geothermal energy is stored in hot water underground.
Now I will discuss about conversion and after conversion.
Geothermal energy can be captured in two ways, in power plants and in heat pumps. As said earlier, there are three types of power plants: dry steam, flash steam, and binary cycle. In heat pumps, there are four types: 3 in closed loop and 1 in open loop. So how do we convert geothermal energy in these two ways? We will answer that question in the following slides. The principle in geothermal energy is simple. The heat generated from the Earth's core heats up the underground reservoir to produce steam, which is then used to produce electricity. Equipment used in the power plant to extract geothermal energy. 2 wells are drilled through the crust of the earth, and pipes are connected for the steam and liquid to travel. 1 production well where the plant gets the steam. This is the main equipment in harvesting geothermal energy. And the other one is in the injection well, where the plant injects back the unused liquid from the production well and condensed steam. The first process of the power plant is in the production well. Steam and superheated fluid are extracted from the production well into the steam generator. Steam and superheated liquid are separated. Steam is then used to run the turbine to produce electricity. The used steam from the turbines passes through the condenser that turns it back into fluid. The unused fluid from the earth and the fluid from the condenser goes through the cooling tower. The cooling tower cools the temperature of the fluid before injecting it back into the earth through the injection well. These are the difference in the steam generator of each power plant, or the different methods each power plant use to extract geothermal energy. First is the dry steam power plant. Steam from the production well is directly connected to the turbine. Next is the flash steam power plant. Superheated liquid from the production well. As it is pumped towards the surface, the pressure decreases, causing a portion of the superheated liquid to separate and flash into steam. And the next is the binary cycle power plant. Its steam generator uses a heat exchanger to heat a second liquid. The second liquid used has a lower boiling point than water. Isobutene as an example. The second liquid is recycled through the turbine and back into the heat exchanger to be used again. Not all geothermal energy comes from the power plant. The principle of geothermal heat pump is also simple. In the summer season, the temperature outside is hot. Hot temperature from the outside is brought underground using the heat pump. Since the temperature just below the Earth's crust is constant at around 50 to 60 degrees Fahrenheit, the Earth absorbs the heat, making the temperature cooler. In winter, the cycle can be reversed. Cold temperature from the outside is brought underground using the heat pump. Since the temperature just below the Earth's crust is constant, the Earth emits heat to the colder temperature, which increases its temperature and making it hotter. Remember that heat travels from hot to cold based on the second law of thermodynamics. Equipment used in the geothermal heat pump to extract geothermal energy. The geothermal heat pump itself, which exchanges hot and cold temperature, and the pipes that are connected to the geothermal heat pump. The process of geothermal heat pump. Water or refrigerant, water and antifreeze for winter season, are used in the system to heat or cool the home, moving through the loops of pipes. In summer season, hot temperature from the outside gets absorbed by the heat exchanger that lets it flow through the pipes. The pipes are then brought underground, which is then cooled by the earth. The cooled pipes are then used to cool the air of the homes, buildings, using the ducts and vents. In winter season, cold temperature from outside gets absorbed by the heat exchanger that lets it flow through the pipes. The earth then warms the pipes that are brought back into the heat pump to heat the air of the home and buildings. There are three types of system in the closed loop. Closed loop horizontal system are the most common and most cost-effective for residential areas. For larger commercial buildings, closed loop vertical systems are more often used. Closed loop constructed under or in a pond or lake are usually the cheapest. In open loop system, the water is taken directly from the water source into the heat pump, where it can either be recycled back into the same source or pumped into another water source without polluting. Thermal gradient is used to find the rate of change of temperature with respect to depth. Since the geographic structure of the Earth is different throughout the world, heat underground is also different in places to places. This equation is used to know the total energy stored in the certain depth and location of that area, with respect to the thermal gradient equation. Coefficient of performance, or COP, is used to find the performance of the heat pump. These equations are used to know the thermal power when the water is rising out of the production well or being injected down the well. This equation is used to find the lifetime of the geothermal field.
Geothermal energy, emissions, and its impacts on the environment.
Geothermal power plants can meet the most stringent clean air standards. They emit little carbon dioxide, very low amounts of sulfur dioxide, and no nitrogen oxides. The small quantities of gases emitted from geothermal power plants aren't created during powered production because there's no combustion. These gases are natural, minor constituents of our geothermal reservoirs. They eventually would vent to the atmosphere without geothermal power development, although at much slower rates. When geothermal power plants do emit gases, it's mostly carbon dioxide, which isn't a pollutant but a greenhouse gas. Still, geothermal power plants emit much less carbon dioxide than fossil fuel power plants. Also, the common practice by geothermal power plants to inject geothermal fluids back into reservoirs to sustain resources has diminished their carbon dioxide emissions. One of the few geothermal energy emissions is hydrogen sulfide. This gas causes the characteristic sulfurous odor evident near hot springs. The impacts to the environment of geothermal energy can be classified into four types. The first one is water quality and use. Geothermal power plants can have impacts on both water quality and consumption. Hot water pumped from underground reservoirs often contains high levels of sulfur, salt, and other minerals. Most geothermal facilities have closed-loop water systems in which extracted water is pumped directly back into the geothermal reservoir after it has been used for heat or electricity production. In such systems, the water is contained within steel well casings cemented to the surrounding rock. Most geothermal power plants re-inject water into the reservoir after it has been used to prevent contamination and land subsidence. In most cases, however, not all water removed from the reservoir is re-injected because some is lost as steam. In order to maintain a constant volume of water in the reservoir, outside water must be used. The amount of water needed depends on the size of the plant and the technology used. However, because reservoir water is dirty, it is often not necessary to use clean water for this purpose. The second impact to the environment is the air emissions. The distinction between open and closed-loop systems is important with respect to air emissions. In closed-loop systems, gases removed from the well are not exposed to the atmosphere and are injected back into the ground after giving up their heat, so air emissions are minimal. In contrast, open-loop systems emit hydrogen sulfide, carbon dioxide, ammonia, methane, and boron. Hydrogen sulfide, which has distinctive rotten egg smell, is the most common emission. Once in the atmosphere, hydrogen sulfide changes into sulfur dioxide, SO2. This contributes to the formation of small acidic particulates that can be absorbed by the bloodstream and cause heart and lung disease. Sulfur dioxide also causes acid rain, which damages crops, forests, and soils, and acidifies lakes and streams. However, SO2 emissions from geothermal plants are approximately 30 times lower per megawatt hour from coal plants, which is the nation's largest SO2 source. Some geothermal plants also produce small amounts of mercury emissions, which must be mitigated using mercury filter technology. Scrubbers can reduce air emissions, but they produce a watery sludge composed of the captured materials, including sulfur, vanadium, silica compounds, fluorides, arsenic, mercury, nickel, and other heavy metals. This toxic sludge often must be disposed of at hazardous waste sites. The next environmental impact of geothermal energy is the land use. The amount of land required by a geothermal plant varies depending on the properties of the resource reservoir, the amount of power capacity, the type of energy conversion system, the type of cooling system, the arrangement of wells and piping systems, and the substation and auxiliary building needs. Land subsidence, a phenomenon in which the land surface sinks, is sometimes caused by removal of water from geothermal reservoirs. Most geothermal facilities address this risk by reinjecting wastewater back to geothermal reservoirs after the water's heat has been captured. Hydrothermal plants are sited on geological hotspots, which tend to have higher levels of earthquake risk. There is evidence that hydrothermal plants can lead to an even greater earthquake frequency. Enhanced geothermal systems can also increase the risk of small earthquakes. In this process, water is pumped at high pressures to fracture underground hot rocks reservoirs, similar to technology used in natural gas hydraulic fracturing. Earthquake risks associated with enhanced geothermal systems can be minimized by siting plants an appropriate distance away from major fault lines. When a geothermal system is sited near a heavily populated area, constant monitoring and transparent communication with local communities is also necessary. Lastly, life cycle global warming emissions. In open-loop geothermal systems, approximately 10% of the air emissions are carbon dioxide, and the smaller amount of emissions are methane, a more potent global warming gas. Estimates of global warming emissions for open-loop systems are approximately 0.045 kilogram of carbon dioxide equivalent per kilowatt hour. In closed-loop systems, these gases are not released into the atmosphere, but there are still some emissions associated with plant construction and surrounding infrastructure. Enhanced geothermal systems, which require energy to drill and pump water into hot rock reservoirs, have life cycle global warming emissions of approximately 0.09 kilograms of carbon dioxide equivalent per kilowatt hour. To put this into context, estimates of life cycle global warming emissions for natural gas generated electricity are between 0.27 and 0.9 kilograms of carbon dioxide equivalent per kilowatt hour, and estimates for coal-generated electricity are 0.64 and 1.63 kilograms of carbon dioxide equivalent per kilowatt hour. Strategies to improve geothermal resources. The first strategy is by the use of cascaded technologies, in which the geothermal fluid cascades first from the highest available temperature for creating electricity down through direct use applications that require successively less heat, including spas, industrial processes, and snow melting, each with distinct temperature ranges. Another improvement is the harvesting of valuable materials from geothermal fluid. In addition to using the heat to create power, techniques are developed to profitably extract strategic minerals from brines via new geothermal mining technologies. The project is validating improved lithium extraction techniques, transform mined materials into saleable products cost effectively. The best way of increasing the value of brines is by improving the efficiency and reducing the cost of power generation technologies. The DOE's Pacific Northwest National Laboratory is in the process of developing microporous metal organic solids as the primary heat carrier and heat transfer medium that could increase power generation at binary plants by 15%. Finally, by using water produced in oil and gas and mining processes, geothermal developers can leverage existing infrastructure and greatly reduce the cost of development, conversely, increasing the value of the fluid stream. This project developed an optimized solution for power generation using co-produced geothermal fluids that will produce a constant 75 kilowatt of electricity. Thank you for listening. Have a nice day.